The Gaussian, one of quantum mechanics' most important tools. Today, we apply it to solve a scattering problem using the Born approximation. How cool of a picture is this? This is from a optics paper, actually, which I'll link below and discuss soon. But as we see, a nice two-dimensional Gaussian, pretty darn cool. All right, so the problem today then is question 20 out of the extras from chapter 10, where we want to use the Born approximation to determine the total cross-section for scattering from a Gaussian potential, where we have V0 as the amplitude, e to the minus mu r squared over a squared, r being the variable. And what we want to do is express our answer in terms of the constants V0, a, and m, the mass of the incident particle, and k, where we can see that we have E, and E is the incident energy. And this is why we care, is because Gaussians are used everywhere in quantum mechanics and all the derivatives of quantum mechanics, such as optics and things of that nature. Very, very cool stuff. Okay, but also the challenge then for you is I would like to discuss the paper that the original image I just showed came from, because they talk a lot about the optics and about the scattering process, things of that. I found it very cool to dive into, but I think a more in-depth conversation would be fun. That being said, this is a pretty straightforward problem, but there's a lot of chunky work. So if you want the PDF, feel free to comment and I'll send you the link to the Patreon page and you'll be good to go. That being said, if you're curious about the world of science, be sure to subscribe. I post educational content every week to quench your thirst for curiosity. So with that, let's jump into stop number 1. Alright, so although this problem is fairly straightforward, we just need to handle things with care and, maneuver, because these integrals are not necessarily easy. That being said, what we need to do is find the scattering amplitude first, which can be done with the help of equation 10.88. Okay, and then once we set this up, we can utilize things like integration by parts, calculators, tables, things like that to help us with these integrals. That being said, we have all the constants we've become used to seeing now, then our potential that we have to plug in. Okay, the thing I want to highlight here is that this exponential is a function of r, sine is a function of r, and then we have an r right here. That's a triple product. That's pretty gross. Okay, so after we shove this potential through the V0, or the constant through, the V0 is good to go. It's out of our way. We really need to highlight on how do we simplify this triple product here. And we're going to use a pretty clever trick here, and I want to highlight how r and this e to the r thing can relate together and save us time. So first, let's investigate this thing and then move forward after that. All right, so first I want to note that if we take the derivative of the exponential, what we see is that we end up with a chain rule event, right? Take the outside, we just repeat the exponential. Inside, you get negative mu over a squared times 2r. Pretty easy there. And then what we see is that when we collect all of these, we get negative 2 mu a squared r, and then r with the exponential. So if we get rid of these constants to this side, what we end up with is this purple beast here. Okay, so what we can do is rewrite r e to the negative mu a squared r squared that's inside the integral in terms of a derivative with constants. The reason why this is helpful is because then you can set up your integration by parts very quickly. Okay, so doing that, we see that upon plugging this in, negative and the 2 cancel here and here, so we get that cleaned up. But then we could take these constants out front, get rid of them now. And now we see it becomes imperative to use integration by parts. This thing here then is the dv stuff. This thing here is u. And so then we have u, v, minus integral v du, right? Integration by parts that we've seen before, but now putting it with the derivative already on it, when we integrate through, it's a lot easier to deal with. So that's pretty darn cool in my opinion. That being said, again, and it's all in the PDF, but that being said, this is a pretty straightforward process now. We just have to be careful with cleaning everything up, especially this bracket here where we need to evaluate. That infinity and that 0 are going to cause some problems in here, so we just have to be careful in handling them. Then we have to clean up this side, and upon doing so, we have more integrals, more integrals to deal with, and then we'll be all right. Oh, that wasn't nice. All right, so evaluating that bracket then, we have sine where we just put infinity there, but the real thing here is that e to the negative infinity goes to 0, so that is all summarized there, so this whole term goes to 0. And then simultaneously the sine of 0 goes to 0, so this exponential goes to 0. So overall, this whole bracket goes to 0, and it gets rid of a lot of our cluster that we would have had. That being said, all we're left with is that this infinite integral here that we just clean up. Okay, then we see that the kappa kappa cancel. We can bring the negative sign out front. And now we're from a 0 to infinity of this kind of form of integral. And I'm lazy and I use the Chalm's book because there is no easy way to do this without repeating integration by parts and creating a general form. So by saving time, referencing Chalm's book here, we can just plug in the form here. Notice that in the square root, I'm dividing by a squared, so that would be, well, we have a fraction in the denominator, so that would turn into a reciprocal, but because it's a square, we can bring it outside, and that's why we see the a up there. So once we tidy this up, then we're good to go. Okay, and so after we're done with that, thanks to the integral table, we see that this is the form we have here. And this kappa we have to be careful of or aware of because that's equal to 2k sine theta over 2, which we've seen before. I think it was 10.89. And that's what makes the scattering amplitude as a function of theta. And because of this bugger up here, this whole thing is going to be a pain in the butt to deal with in referencing the total cross section. So just prepare yourself for that. And of course, if you're finding this helpful, don't forget to give it a thumbs up. It helps more curious minds like you discover this content, and then we can grow this community together. So with that, let's jump into the cross section. So then stop number 2 comes in, and our familiar friend equation 10.14 comes in, and we see that we can obtain a cross section, just, separable variables, integrate, things like that. We see that upon doing so, we need to clean all of this up first. Clearly, we have a magnitude squared. We have, distributing the sine, the 2k sine theta over 2 squared from the result from the last part. We cancel the 4's there, easy enough. The theta part of the solid angle has sine theta d theta. The phi part has d phi. Clearly, Fubini's theorem right now will allow us to clean that up. Noticing here that the absolute values here go to brackets here, but we just get rid of the negative sign because it's absolute value. And then we just need to put the square on everything, which I'm doing the red on purpose to highlight how the squares affect everything. And then eventually we'll clean this up. Now with this, the square root goes away and then we just multiply the exponential by 2 since we're squaring it. Same rules that we've become accustomed to. The big thing here to note is that this is a sine of theta over 2, and this is a sine of theta here. So the way we can handle that is by using the half angle identity and putting 2 sine theta over 2 cosine theta over 2 into that sign, and then we set ourselves up for a great substitution here. Okay, so clean this all up. That 2 cancels with one of those 2's that we now took outside of the integral. This phi integral just goes to 0, or phi, so 2 pi minus 0 will leave us with 2 pi. You could jump straight to that if you wanted to, but here, then, now we're just left with trying to tidy up this green integral, and that's where we're going to spend most of the time from now on. So, as promised, we have 2 and 2 canceling, so that pi will just be up there. We have our setup here for the substitution now that we're cleaned up. And as such, we're going to let x equals sine squared theta over 2, which, if you're not used to the notation here, that's just a square on the outside. Then our dx term would be, well, now we have a chain rule event. Bring the 2 down, leave the inside alone, times the derivative of the inside, times the derivative of the inside. So 2 and 1/2 cancel. Be very careful on this step. 2's are being flown around everywhere, so just clean up as you go. And of course, if we're going to do a substitution, let's go ahead and clean up the limits. Sine of, or x evaluated at the upper limit brings us to pi over 2, which sine of pi over 2 is 1. So 1 squared is 1. Same thing for 0. We just get 0 squared, so 0. So that our integral now takes the form of this. Okay, and we're good to go. And after doing so, what we observe then is this pi goes and joins the one we had up top anyways. And then we're from 0 to 1 on our limits, and then we get 2k²a² over mu, x, and then dx. We're able to get rid of all of that stuff, all with one single substitution. However, this still looks like a mess. So in doing so, let's go ahead and do another sub just to clean it up. Theoretically, you could do this all in one foul swoop, and I almost did that, but then it just became too clunky in typing it. So a couple separate steps made it a little easier. So if we let t be everything inside the exponential, then our dt is just equal to all this dx. Solve it for dx. We see we're just pushing that over. No big deal. You're reevaluating the limits. You're just plugging in 1 and 0 respectively, and we see that these are the results we get. Not too bad there. Pretty typical integral. You don't really need to do this step if you're comfortable with your antiderivatives. If I'm multiplying in here, I need to divide outside, things like that. But a good substitution never hurts. So let's see how we simplify this now. So now that we have that substitution, our limits get reordered here. Good to go as expected. E to the t is now there. Now our dx term turns into this. I'm purposely color coding this negative here because what we're going to do is switch the limits here for the negative sign, which we're allowed to do. And then we're just left with e to the t dt inside. All these constants can come outside. We now see that this mu will cancel with one factor of the cube here. This a² will reduce that 6 to a 4, 3 to a 2, so we get a nice tidy up of constants out front. Now we're just left with a basic integral. E to the t goes to e to the t. Evaluate at the boundaries. So that's e to the 0 minus this clunky thing. Thankfully, we know that after we clean up all the constants, put them in cleaned up order, e to the 0 is just 1. That's what we see here. And this thing is just no way to clean up, so we're just going to leave it like that. And thus, reorganizing all our constants into the terms we want, we see that the total scattering cross-section is pi² m² v0² a to the 4th over 2 bar to the 4th mu² k² with this ridiculous thing here. But what we see about this and why I think it's important is because with a and mu, with those parameters and the energy, as the energy from k gets bigger, we see that this thing is going to be smaller. So that is going to be that's going to tell us a lot about this, because if this thing gets infinitely big in the exponent, then this whole term gets small because of that negative, and then we're just left with these coefficients. So pretty darn cool insight there. All right. Well, thank you for listening to my rambling. That was more of a mathematical style problem and just working through integrals. But knowing that Gaussians are so important to quantum mechanics, I found that that was a very necessary application to look over again, especially referencing how to do those integrals and the little tricks that come with it. That being said, this kind of setup is definitely used in a lot of the optics and photo optics due to the Gaussian wave packets that are often used for photons. So that's why I referenced that optics paper before, and why I think that looking at this now, it might not seem like it's useful to you, but Griffiths has a way of putting things in places to where you see them later and you're like, I'm glad I did that, without showing you exactly why. And this is another one where I think that is the case. So that being said, if you like this, please share with a friend who's also curious about science, and let's grow this learning community together. I think this has been a wonderful project in this chapter. This will be the end of chapter 10, and then we get on to quantum dynamics in chapter 11, which will be really, really fun, or really, really painful, depending on how you like perturbation theory. That being said, thank you again to all the supporters of this channel. You make this possible. Please consider supporting this channel by subscribing and sharing this curiosity, joining the Patreon page, or donating to the Buy Me a Book Club via Buy Me a Coffee. However you can, just realize that I'm grateful for everything, because without you, this is not possible. As always, thank you for watching, and until next time, stay curious.